Yeah, before starting, I just wanted to understand how many of you already know what Blink is? One, two. Okay, perfect. Perfect audience for this talk. Again, so Blink is the rendering engine. It is an open source rendering engine that is created by Google. I will try to do is try to explain what it does. It is a very very high level explanation. It is not, I'm not going into how the code works or yeah, how everything works. And this part, I'm just trying to make sure that you understand how HTML and CSS gets converted to pixels on the screen. We are not going to be talking about how updation works, how compositing works. I'll explain everything in detail of what those are in my next talk of how updating happens, how JavaScript influences it. But for this, let's just go ahead with and understand how HTML and CSS gets converted. Okay. Okay, this is a little bit about me. I am Siddhant. I am not sure if anyone calls me Siddhant. Most people call me Sid. But my Twitter handle is right here. I'm very active on Twitter. If you want to reach out, if you want to listen to my, if you want to read my tweets, I just post a little bit about engineering, mostly about product engineering. And this is my email if you want to reach out to me. I work as a front-end engineer at Nirvana Tech. All right, let's start with the questions. What do you think renders the pixels on the screen? Any hands? Nobody knows what renders pixels on the screen. On the screen of the computer, what renders the pixels? There are only two parts that can render render pixels. One is a CPU and the other is a GPU. What do you think renders? GPU, yes, correct. You all are engineers, right? I need voices. You all have done engineering. You know all this stuff. So yes, GPU is responsible for rendering the pixels on the screen. And does anyone know which library is responsible for rendering? No one? Okay, I'm doubting everyone now. But yeah, the OpenGL library is responsible. So it is an open source library that is created, and OpenGL is Open Graphic Library that is responsible for getting commands from the operations and converting that giving commands to the GPU to render. So it sort of acts as a middle layer. It is an operating system. So it is not an operating system library. It gives commands to the operating system to render to the GPU. Last question. Are there any other libraries that can also be used? I didn't get a response on the last question. I am assuming no one will know this. So the library that is being used nowadays is called Vulkan. OpenGL and Vulkan both are similar libraries. They have a little bit of difference. If you want to understand, let me know. All right. So all of us work at this layer. We work at HTML and CSS. What we want to go is we want to go deep. We want to understand how the HTML and CSS gets converted to GPU level operations and how does the rendering happen. So this is the entire task of the Blink rendering engine. It is to convert your HTML and CSS to give operations to the GPU, and then the rendering happens. So this, in very high level terms, is your job of the Blink. There is, so yeah, let's start with this. Everything inside the red border is the content. Other than that, nothing is content for the Blink. So whenever Blink is rendering, it takes care of only this red part. And when Blink renders, it renders inside a sandbox. So this is a security model that is proposed by the open source community, and the Google pioneered it. In the sandbox, you have the Blink engine and the Chromium compositor. So the compositor is again a different thing. I'll explain in my next part of this talk what does a compositor do. But for now, we will take care of how the Blink engine is doing everything. So this security model is therefore because there can be vulnerabilities inside the rendering code. So no one can take advantage of that code and render anything on your screen or do any sort of malicious. So it's just a security model. If each rendering happens inside a sandbox, this will come in handy later. Right. So it's we are now getting into the weeds of thing. Our goal is to convert content into OpenGL calls, and the OpenGL call will call the operating system and give instructions to render on the GPU. Right. The goal for Blink is to convert content into pixels and to create data structures for efficient updations. Because if we run the entire Blink code again and again on the updated code, our page will be janky. So these are the two goals of the Blink rendering engine. So the first step, how many of you know about DOM? Awesome. Okay. So the first process that happens is converting HTML to DOM. This is the first process. When the HTML is downloaded, it hits the Blink parser. So this is an example that I have drawn in Excalidraw. So the HTML is there. It goes to the HTML document parser, and the HTML document parser releases intermediate data structure, and it goes to the HTML tree builder, and you get a C++ version of a DOM tree. So this is exactly what DOM is. And the C++ DOM tree acts as an internal representation for Blink and an API for JavaScript to work with the DOM. And this is available via V8 through something called bindings, where you can pass JavaScript queries and it will convert those to bindings and work on the C++ DOM. And I'm giving you a task, read more on how Shadow DOM works. So if you have heard about web components, you can create your custom components and Blink takes care of that. How does Shadow DOM works inside of this? This is again a different conversation, but if you want, you can go ahead and read this. Next, so we have converted our HTML to our DOM. The next is how the styles come into the picture, because these are important for rendering as well. We can't render without the styles. All right. So this is a very basic example of, we have a style rule is applied, and the color of the P tag gets converted to pink. Right. So again, we have another parser. We already had a parser called the HTML parser. We created a DOM tree, and we create another object model called CSS object model. This is called CSS OM. I didn't know about this previously. The CSS parser again creates a new data structure called the style sheet contents, and the style sheet contents have all the CSS rules. So we had two parsers up till now, HTML parser and the CSS parser. The CSS parser convert every rule to a style sheet content using the properties that are already predefined inside the C++ compiler. So the next step is the style resolution engine. So there can be multiple style sheets and there can be conflicting styles. How does a style resolution pipeline works? So you have the style resolver. This is the C++ code, and you have the style sheet contents. The style sheet contents is the content that was generated in the previous parsing step. You have the style resolution, style resolver plus the style sheet content plus your C++ DOM tree, and you get computed style for each of the DOM node. I have given a link on how styles are resolved. This is again a deep conversation on what are the checks that Blink does on which style should be applied. I'm not talking about it here, but it gives this step gives each DOM node a style. So this is called the computed style, and you can see that in your Google Chrome DevTools. When you click on any DOM node, go to the computed tab, and you can see all of the computed properties that the Blink is given you. This is directly coming from this step from the Blink engine. All right, we are done with the HTML parsing. We are done with CSS parsing. The next step is laying out, because the browser doesn't understand what Flexbox is or what CSS grid is. It needs to know what X is, what Y is, what height do we need, and what width do we need. So this is all the information that we need to give to the browser to understand, or to the GPU to understand. There are two types of flows that happens, and this is what the layout step of the Blink engine tries to accommodate. One is the block flow. This is from top to bottom. All the blocks flow from top to bottom, and there is an inline flow. If you go into span flow from left to right. In modern English languages and in Arabic and Hebrew, they flow from left to right to left. So this is what the next step will come in on and how this goes. But the layout step has two steps. And now we have to understand how text flows inside the layout, because this will all decide on our next part on how the next tree gets made. So there are a lot of trees inside the Blink engine. So there is an open source library called Harfbuzz. Google uses this to calculate what each layout of each glyph would be. So you get all the text, and this library tells you where they should render, what is the width and height of each pixel of each glyph. Now we get to another tree called the layout tree, and these all layout view objects are these all layout views. So you can see the document is a layout view, HTML is a layout block flow, and body is a layout block flow, and P is a layout text, and all of this stuff. These all are childs of layout object, which is a parent class, and this is currently in the middle of a rewrite. I've written in the bottom, you should read on shadow roots, on how shadow roots get made inside the layout, and layout ng mixins. So layout ng mixins are the next generation rewrite that is happening. So this is an incremental feature that the Blink engine is rolling out. So you should read about this as well. Okay, when the layout tree gets made, we now have to create physical fragments, and these include line breaks and content breaks. So what we have till now is, for example, there is an entire page with just one P tag. And in that case, only one layout text will be created in this case. But that using the Harfbus library, we now understand that the text can flow on different lines. So this is where it comes in. From the input from the Harfbus and the layout tree, we create another tree called the fragment tree, and the physical fragment tree can flow on different lines. So for example, each line has a different fragment tree. Each line has a different fragment child, and you get a fragment tree. Again, read on shadow roots and layout ng mixins. Right. So now we have a layout object. What we have up till now is HTML parser, CSS parser, layout, Harfbus, and the fragment tree. So 5 steps are done. The next step is the paint ops. So now what we have to do is physically render that fragment tree on our browser, because we haven't reached the pixels yet. We are very high level till now, but this is where we go deep. Now each layout object has a method called paint, and this paint method runs on every updation and on initialization. What this paint method does, it creates artifacts, and artifact is a high level data structure, and in that we have display item, and in display item we have all the geometry of what we have to render. So I can go ahead and show you an example. Okay, this is working. Yeah, so the paint uses a different order called the stacking order, because stacking order can be controlled using Z indexes. And this is how the rendering happens. First the background is rendered, then the floats are rendered, then the foregrounds and the outlines. And this can be controlled using Z indexes. So this is a very small example of how the paint op is displayed. So you have a box, you can see right here. You have a box, inside it has pixels and it has a purple border. Now these are the 3 paint ops that are being calculated. The first is a drawing document background. This basically fills the entire document. This fills the entire document with a white color. So this is the first paint op. The second is the drawing box decoration background, and this is the second paint op. What it does, it draws a rectangle first and fills it, and it then draws a stroke. These are again very high level paint ops. We are not going into how these paint ops work inside, but these are very high level paint ops. And then we draw the pixels on the screen. So this again uses Harfbus library and calculate what should be the width of the glyph. Awesome. Now we have the next step, that is rasterization. How many of you know what rasterization is? Oh, awesome. Computer graphics ke students kaun hai yahan pe? Okay. So rasterization is a process in which we convert paint op and pass it through a method called raster, and we get a bitmap. A bitmap is basically ones and zeros, and it has all the information inside it. What it does basically is it gives you what pixels do you want to render on the screen, and this happens inside the GPU memory, and this process is called hardware accelerated rasterization. You can enable it or turn off. If you turn it off, your rasterization will be a little slow, because first the rasterization step happens on the CPU, and then it gets passed on to the GPU. So raster also converts images to bitmaps. So you have EXIFs, it converts JPEGs, PNGs to EXIFs, and you can render that on the screen. There is a command that you can use to see that. Awesome. So after paint, we have raster. So up till now we had HTML, CSS, layout, paint, and raster. We have 5 processes, and now the bitmap is created, 6 process, and then the paint op takes another use of another open source library. This is again maintained by Google, and it takes the bitmap and it takes the paint op that we already had, and it uses a library called Skia, and the Skia takes paint ops and bitmaps and generate low level OpenGL commands. Yeah, and so again, it takes care of blend modes, anti-aliasing. So blend mode is basically how it will look on the screen on how the different colors will overlap, and anti-aliasing is basically smoothing of the rough jagged edges. So because in rasterization is not vectorization basically, so you have jagged edges in bitmaps. And then when you get the bitmap, you get the paint ops, pass that to Skia, and it issues OpenGL commands. But there is again a problem in this, because everything is running inside of a sandbox, and you can't issue operating system level commands from a sandbox. So now we have two processes. One is the renderer process, and the second is the GPU process. The first, the raster interface passes all the paint operations inside a command buffer to the GPU process, and inside all the decoding and the rasterization happens. So, and the raster operations runs inside the GPU process. Again, you can see the example here. I know it is a little confusing, but let me know if you want to understand how it works deeply. Raster, so that impl, ignore that. That is a convention of what we, that will come in the next part of what impl is. But yeah, basically it puts all the operations in a GPU command buffer and passes that to the GPU process. In that, the rasterization happens, pass that to Skia, issue OpenGL commands. But there is a problem. In Windows, OpenGL doesn't work. It does work, but we get a better rendering experience with DirectX because it is natively supported. So there is another library called the Angle, and again, this is made by Google, and it converts OpenGL commands to DirectX commands. And now we are into the weeds of how the rendering happens. So DirectX is an operating system level command. It issues operations to the GPU, and it renders pixels on the screen. So this, in short, is a review of how the Blink engine is working. The first, we have the DOM process, then the style, layout, paint, raster, GPU, and now we have pixels on the screen. So we haven't covered how updation works inside this, how JavaScript is working, how animations are working. Again, I'm not touching updations because that is where the compositor will come in. I don't want to talk about it today, and we are done finally. And I'm still working on part 2 of this. If you want to get updates, you can again follow me here, and I'm done. If you have any questions, please ask. No questions? Did you guys understand everything, or do you want me to go through it again? No? Okay, you can ask me questions personally. Cool. Thanks, guys.